Oh. Welcome, PCS members and friends, to our first PCS IBS seminar of 2024. Happy New Year to you all. May it be successful and healthy. And it's a pleasure to host today Dr. Glenn Wagner from University of Zurich in Switzerland, who is visiting us today. And our scientific host is Zung, who will introduce our speaker.
So, we're very happy to have Dr. Glenn with us for this week and a few more days next week. And he is a brilliant young researcher. He graduated from University of Oxford under Professor Steve Simon, who was very famous on fractional quantum Hall and topical quantum computer. And then he moved to University of Zurich at a postdoc under Professor Titus. He also very famous on typical phases of matter, especially he's one of the person who wrote the first paper on fractional chain insulator. And Glenn's also very famous in the community with some of his work on twisted bilayer graphene, where he found a few exotic phase twisted bilayer graphene that's discovered also in experiment. And today he will give us a talk on a different topic on kagome metal. And let's welcome our speaker. And Glenn, please.
Thank you. So, yes, today I'm going to be talking about correlated order in the so-called kagome metals. So at the beginning of my talk, let me just start by thanking my collaborators for this project. So as you mentioned, I'm at the University of Zurich, and I collaborated with Mark Fisher and my postdoc advisor, Titus Neubert, on this project. We did the theory together. And then on the experimental side, we collaborated with Philip Moll's group at the Max Planck Institute in Hamburg. So let me give a brief outline of today's talk. I'll start by introducing the so-called kagome metals. I'll talk about some of the experiments that have been done. And in particular, I'll focus on the charge ordering, which will be the main focus for the rest of the talk. Then I'll present to you the experimental results that our collaborators obtained, that were looking at one specific transport anisotropy, and they got some surprising results. And I'll explain in the second half of the talk how to explain these results using Landau theory and what these results tell us about the nature of the charge order. And just to give you the punchline before I start the actual talk, so what we find is that even though the pristine system has got some C6 rotational symmetry, very small perturbations are enough to tip the system into some symmetry-broken phase. And these perturbations are either some strain fields or some magnetic fields. And our conclusion is that this material is just very sensitive to these small perturbations, hence why we call this material at the tipping point. And we managed to reproduce this experimentally observed phenomenon with our Landau theory. So here you can see a measure of the anisotropy plotted in this three-dimensional space where one axis is the strain, one axis is the magnetic field. And you can see that along this axis where strain and B field are zero, your anisotropy is zero as well. But as soon as you add these perturbations, you increase the anisotropy. And I'll explain to you why that is that these perturbations lead to the anisotropy. And I should say that the magnetic field here that we consider is an out-of-plane magnetic field. So it's not breaking the C6 symmetry. I mean, otherwise it would be somewhat trivial, but the magnetic field does not break the symmetry. It's
That's a strain wind breaks the CC.
the strain breaks it explicitly. So that part is not so surprising. It's more the magnetic field that is surprising.
You have a model includes the phonon effect or in electron.
So we're just going to build a Landau theory. So actually, we're going to be agnostic about what the cause of the instability is, whether it's phonons or whether it's electrons. We don't know, and so we're just going to build a Landau theory that's general based on symmetry principles. So let me start by introducing these materials.
Sorry, can you just comment? So again, the strain is obvious body that you can break the symmetry. What do you mean by magnetic field? And it's not in internal system preservation. What do you mean by that? You add magnetic fields and then that will break these.
You apply a magnetic field.
You apply, but you have to apply it.
Exactly.
So it's not a real instability thing per se.
No, it's just an applied external field that
Which will do things.
Yeah.
And what is then the surprise that in principle a magnetic field is so to say invariant under all these C6 or whatever.
Exactly. The magnetic field itself does not break the C6 symmetry. But I'll explain that later how that comes about.
But it depends on the direction of the magnetic field.
Right.
You are along the C-axis.
It's along the Z-axis.
But you're applying the.
Yes. But our experimental colleagues were very careful to make sure it's really aligned along the Z-axis and not no in-plane component. So the kagome metals usually refer to this family of 3 different materials, actually, where they've got the following chemical formula, where you've got some alkali atom, which is either potassium, cesium, or rubidium. And then you've got this vanadium, which sits on a kagome lattice. So it's really the vanadium that forms this kagome net. So you see an illustration of one of these compounds here. This is the potassium-based compound. And you can see the red atoms are the vanadium atoms that sit nicely on a kagome lattice. It's a sort of layered material. So each of these layers forms a kagome lattice, and then you stack these layers on top of each other. But for the rest of the talk, I'm going to mostly just work in the 3D plane, and I'm going to assume that the 3-dimensional physics is not so important. And furthermore, if you just write a simple tight binding model for the orbitals on the vanadium sites, then what you find for just a single orbital model on the kagome lattice is the following band structure. It's basically the band structure of graphene with the Dirac cone plus one perfectly flat band. And what you notice is that you've got these Van Hove singularities here at the endpoint in the Brillouin zone. And it turns out that the charge order that we get is exactly modulated with this momentum of the endpoint vector. So it's somehow coming from the Fermi level being close to these Van Hove singularities that we have this exact type of.
The flat band is not topological, right?
Sorry?
The flat band is not topological.
This flat band, no, it's just coming from some interference effect when you go around these kagome sites. Yeah.
Why is it in the top and not in the bottom? If I remember correctly, for kagome. It's the wrong thing.
So if you
This is the rate of the hopping sign.
Sure, but that's exactly my question. So why is the hopping? Then let me rephrase my question. Why is the hopping sign different from the normal one?
Oh, so this is just a very simple type binding model on that particular lattice, but I'm not claiming that this is actually what the band structure looks like, because actually it's not a single orbital, it's more complicated.
So that's on the kagome.
That's just, if you just write down a simple type binding model on the kagome lattice, you will.
This is just p orbital, not s orbital.
That's why the sign is different, right? Okay.
Good. So why is there so much interest in these kagome metals? So really, there's two different experimental observations that triggered this interest. And the first experimental observation is that you get some kind of charge order. So one of the ways in which this shows up in the experiment is that if you measure the resistivity as a function of temperature, you see there's some kind of kink at about 100 Kelvin. And I'll show you later some evidence that this is where the charge order sets on. And then if you go to much lower temperatures, you can't see it that well on the scale, but the resistivity drops to 0 at some small temperature. So this is just zooming in to small temperatures so that you can see this drop better. And what you can see is that there's a superconducting phase with a TC of about 2.5 Kelvin. So there's charge order and superconductivity. And of course, there's been a lot of interest in this superconductivity as well, trying to understand the mechanism behind it. That's still an unsolved problem. But I'm not going to talk about that in the rest of the talk. I'm going to focus on the charge order.
Sorry, how do you see the charge order from this point?
So from this plot, it's not clear. I mean, it's clear that something happens at 100 Kelvin. It's not clear that what happens is charge ordering. But I've got some experimental results from later that will demonstrate this quite convincingly. And the experiments that I will show demonstrate three different things about the charge order. They show that the unit cell increases by a factor of 2 in both directions. There's some kind of time reversal symmetry breaking associated with this charge order, and it's a first order transition.
Happening
At this 94 Kelvin. Yeah. So let me show you the evidence for these three things. So the first one is the fact that you have a 2x2 increase of the unit cell. So the best way to see that is to do STM. So this is STM on the surface of one of these kagome metals. And you can see that there's some kind of translational symmetry breaking. You can see that some of these vanadium atoms have a higher intensity than others. And it basically forms the Star of David pattern, which increases the unit cell by a factor of 2. So the normal unit cell would just be sort of one of these inner hexagons, and now you see that it has increased the unit cell size. And the best way to see that it increases the unit cell is to just do a Fourier transform of this picture, and you can see the peaks corresponding to the undisturbed system in blue, and then you can see these additional black peaks showing up in red. And you can sort of convince yourself that the distance of these red peaks is half of the distance to the blue peak, so it's a doubling of the unit cell.
So in terms of microscopic, it's okay, but you say that it will use Wood-Landau theory?
Yes.
And in this case, how can you have this length scale?
So I'll show you later how we do a symmetry analysis, and we take into account the fact that the unit cell increases by.
So basically, you use this for your Wood-Landau theory.
We built it in the fact that it increases by 2.
Okay.
Yeah.
So in the previous plot of resistivity, what is the Fermi level or Fermi energy or chemical potential? Say?
So for this experiment, this is all for the undoped materials. So
Zero.
the Fermi level is somewhere here, basically.
above the intersection point.
Yes.
You do not consider triple symmetry breaking.
Sorry?
Some people consider nematic, right?
Yes, nematicity. Yes, I'll comment on that later. Yeah, yeah, that's going to be important for this talk, actually. Good. So this is just another plot trying to make this point a little bit more clear. So this is the translationally symmetric system of this cesium compound, and then below the charge ordering temperature, you get this onset of translational symmetry breaking, which can take two different forms. It's the Star of David or trihexagonal pattern. In both cases, we have a 2x2 increase of the unit cell size. Good. Then the next thing I mentioned was that you get some time reversal symmetry breaking. So there's two different probes that have seen this. The first probe is some USR experiment where you see the onset of the signal below some, they call it here T primed. So the charge ordering temperature is about here, and then below T primed, you see this onset of this quantity, which is supposed to signal time reversal symmetry breaking. And the other one is curve rotation, so shining light on the material and seeing the angle by which it gets reflected, and that's another measure of time reversal symmetry breaking that again increases, and it increases slightly below.
But
charge
rotation, you can have this without time reversal symmetry breaking. But if you break the mirror symmetry, you also have curve rotation. So time reversal symmetry breaking can have curve rotation.
Yeah.
Curve rotation is not the other way around.
Right. But then, yeah, there's other signals of time reversal symmetry breaking, like some giant anomalous Hall response as well, and this MUSR. So there's at least 3 different experiments that see these signatures. But it is a little bit controversial because other experiments don't see so much time reversal symmetry breaking. So,
but like curve rotation, you can have without
by itself is not enough.
Yeah.
Good. And then finally, I mentioned that the transition is first order. So the way you can see that is if you tune across this transition, and in NMR you see some first order jump in this night shift. You see the X-ray, the sort of additional gag peak that shows up corresponding to the translational symmetry breaking also is pretty discontinuous here. And then there's some peak in the heat capacity, which is also usually associated with first order transitions. So we have these 3 different experimental facts: the fact that it increases by 2 by 2, the fact that it has time reversal symmetry breaking, and the fact that it's a first order transition. And we're going to bake all of these things into our Ginzburg-Landau theory. So finally, there was this question about the nematicity or rotational symmetry breaking. And indeed, there's a lot of different works that claim to see some kind of rotational symmetry breaking. This plot is showing just some of these works. They're measuring various order parameters to measure this rotational symmetry breaking. But what they all have in common is that they see some kind of increase as you lower the temperature. Some of them only see this increase below some T primed again. Some of them already see the increase at the charge ordering temperature. And our experimental collaborators were trying to really pin down, why are these different experiments seeing different things? And is this really intrinsic to the material, or is it some kind of experimental artifact? Because what can happen in these experiments is that your kagome metal is sitting on top of some substrate. And now you cool the whole thing down. The substrate and the device, they have some thermal contraction going on. And as you lower the temperature, you can imagine that the thermal expansion coefficients of the device and the substrate are different. And this will introduce some strain in your device. And so this is a way that you would get rotational symmetry breaking that increases as you lower the temperature. It could just be an artifact of your device sitting on a substrate and the substrate just contracting at a different rate. So the key question we had is this rotational symmetry breaking really intrinsic, or is it just this experimental artifact? So to determine this, the experimental collaborators made 3 different devices. And one of them is pristine, meaning there's no strain as a function of temperature. And the way they make sure that there's no strain is they have some special glue on this material that dissipates any kind of strain that you might get. So this is really the strain-free sample. Whereas typical samples that most people are working with are these just typical devices which have the strain because of the phenomenon I was explaining before. And then finally, they have a sample where they applied an out-of-plane magnetic field.
So why are not all experiments done with this special glue?
Ideally, they would be, but yeah, this is quite hard to manufacture. And I think this was the big achievement of my experimental collaborators that they actually managed to make these pristine
Then you
samples.
would just say, then let's just remeasure everything with that, but that's maybe so easy.
I mean, that would be the goal, exactly, that everyone uses these pristine samples. Yeah.
The magnetic field is in the case of the pristine sample, so with the glue.
Both.
Or both.
They actually manufactured. They can just apply the magnetic field to these.
Both.
Yeah. So this device here you see is device S3, which is strain free, so it's the same device as this one.
And what is S1?
S1 and S3 are
Both.
the curves kind of lie on top of each other. One is dashed, one is solid. You can.
No, it's both strain.
They're both pristine. Yeah, they just made sure that they could reproduce it. So what they measured is the resistivity along these three different directions as a function of temperature. And of course, if there's no rotational symmetry breaking, you expect the pink, yellow, and blue curve to all lie on top of each other. And indeed, for the pristine sample, you can see that they perfectly lie on top of each other. So there's no rotational symmetry breaking. Now, in these typical devices that have this strain artifact, you can see that as you lower the temperature, at some point, they start deviating and have some strain. And finally, when they apply this perpendicular magnetic field, they also see the same effect, that you get some rotational symmetry breaking at low temperatures. And this was really the thing that we wanted to understand. So, as I mentioned, we now try to build a Landau theory to explain this anisotropy when you add the strain and magnetic field perturbations. And to build a Ginzburg-Landau theory, we could do two different approaches. On the one hand, we could really start from a microscopic model. And I want to show you that this is a little bit hopeless by showing you the DFT band structure of this material. So you see this is the sort of range of energies close to the Fermi level. And you can see it's a bit of a mess. There's a huge number of bands close to the Fermi level. And it's coming from a bunch of different orbitals on the vanadium atoms. And our sort of single orbital model that I was flashing on one of the first slides is clearly not representative of this complex band structure. So instead of trying to solve some microscopic model, we're just going to build a Landau theory, which is based on symmetries of the lattice. So this is the kagome lattice here, and I'm showing you the symmetry operations of the space group. So you've got these translations, you've got two mirror planes, and you've got the C2, C3, and C6 rotations. And we're going to construct order parameters that transform under some irreps of this space group. But the special thing that we have to do is, because the unit cell has increased by this factor of 2 in both directions, we need to also consider representations that transform non-trivially as you translate along these different directions. So here I'm showing you two examples of these order parameters. So let's look at the bond order first. So the bond order is basically an increased hopping strength between certain atoms. So the solid lines here mean that the hopping strength increases along these bonds, and the dashed lines means that the hopping strength decreases along these bonds. And you can see that the unit cell has doubled. For example, if I translate by one unit cell in this direction, I go from plus hopping to minus hopping. And this is illustrated in this this kind of character table. So you can see that delta 2, if you translate by T1, picks up a minus sign.
But this is the T2 orbital. It is three folds. This is three orbital state, right? And the main hopping is driven by the maybe PG's high type hopping. You do not consider that you treat the S orbital treatment, right? But the real better paradigm is T2G. It may be T2G orbital. T2G orbital hopping is the direction. And this shape is like
Right. Yes.
you do not consider the
So I mean, here we're just going.
Symmetry in the
Here we're just going to build a Landau theory of these order parameters, and we're not going to look at the underlying orbital structure. We're going to, I mean, these order parameters could come from different orbitals in principle, but all we care about is the sort of symmetry under these different space group operations. So this so far is completely general for any type of orbital.
So what is special about the T1 and T2? Because it was expanding the lattice by 2. So what is special about this translation?
So I'm just saying that these order parameters transform non-trivially under translations. So usually, if you have a unit cell that has this size, then translating by one unit cell doesn't change the order parameter.
Okay.
But here we consider more general forms of order parameters that can actually transform non-trivially under translations.
Okay.
So we sort of expand the usual space group with these 3 different translations.
So if you translate twice, you come back, but
if you translate twice, you come back to the same. That's right.
okay.
I mean, you can check that, if you translate once, you pick up a minus sign, and then if you square it, you get back the same thing. Good. So once we have these order parameters, we can write down the most general Landau theory, which is taking the order parameters from the slide. So we've got now some bond order that has 3 components for these 3 inequivalent bonds. And then we've got the flux order that again has 3 different components. The flux order is just, you can think of it as, some directional hopping along the bonds. And in total, we have these 6 components of order parameters. And to build the Landau theory, we just need to form combinations of these order parameters that are transforming trivially, and so we can add them to the free energy. And if you do that carefully, then these are the terms that you find. So these are a lot of different terms, but I'll simplify it later and show you what the effect is. But the main thing I want you to notice on this slide is just that these terms come in 4 different forms. There's just the usual quadratic terms that change sign at TC. There's some 3rd order coupling, which I'll talk a lot about in a bit. There's the magnetic field coupling, which couples the bond order and the flux order. And finally, there's the strain, and the effect of the strain is the simplest to understand. So you can see that strain is just changing the TC essentially of delta 1 and delta 2 and delta 3 separately. So this is exactly this explicit rotational symmetry breaking that we expect to come from the strain.
So basically, you also need to consider the time reversal symmetry to consider the second term, right?
So there's time reversal symmetry in here. So that's why delta appears quadratically here. So this term is even under time reversal, and this is why you couple delta and delta prime. This one is odd under time reversal. This is odd under time reversal. So
the cube terms are not possible because of the time reversal. The delta prime cube.
Delta prime cubed is not allowed because of time reversal, exactly. That's right. But delta cubed is allowed. Okay. So as promised, I'm going to simplify this now so that it's a little bit more clear to see what's going on. So for now, I'm just going to forget about the fact that they have 3 components and just consider a 2-component order parameter, delta and delta primed, with some delta cubed term and some delta primed squared term. And we want to consider what the phase diagram of this Landau theory looks like. So one thing to notice is, okay, what happens when you go below TC? Well, this coefficient becomes negative, and that induces some delta. So this is the usual thing. Above TC, you have some potential that looks like this, and then as T is below TC, you get this Mexican hat potential, and that induces some delta. So on the x-axis here, I'm plotting TC minus TC prime. So I'm sort of tuning the relative TCs of the bond order and the flux order. And so what happens on the right is that I cross TC and I induce some delta via this thing here. And I don't induce any delta primed. And then at some lower temperature, I now go below TC primed as well. And then below TC prime, I also have delta primed. So we enter this phase where time reversal is broken, whereas this phase has time reversal preserved. Okay, so this axis is fairly easy to understand. We just have delta and then at TC and delta primed at TC primed.
Maybe too quick. I think that we have 3rd order rather than 4th order.
Okay, so there's some 4th order terms here that I'm neglecting, but the 4th order terms are always there.
But with the 3rd order also, the Mexican head is not symmetric.
That's
It needs
true.
to be tilde. Mexican head will be tilde.
Isn't it even not a head?
Huh?
Isn't it even not a head?
It a head, but it
No, because cubic is like this. So I mean,
so you need
you have
to
a head on one side and no head on the other side.
no, I mean with Q to the 4th term or delta to the
I'm
4th
not
term.
getting
is
something.
valid.
So there's always going to be a delta to the 4th term. I'm just not
Yeah.
writing it here, but it's always there. And so this is why the Mexican hat is always sort of,
Some kind of
Goes up.
asymmetric.
but because of the 3rd order term, yeah, you could have something like this. Right, but actually the more important effect of this 3rd order term is actually that it makes the transition 1st order. So without the cubic term, it's just going to be a 2nd order transition, but with the 3rd order term, it becomes 1st order. And remember, from the experiments, we know that it's 1st order
It's got a
transition.
jump, right? It's got a jump of the terms.
There's a jump, yeah.
Why do you call it a head? I mean, for that you need 2-dimensional control parameter space.
Right. I mean, here I'm just plotting it along some 1-dimensional axis delta. Okay, so that explains sort of cutting along this axis number 4, and you can see this is what it looks like. You have some delta order parameter switching on at TC, and then if TC primed is very low, then you never get TC primed.
So again, TC is the charge ordering.
TC is the bond order, and TC primed is the flux order. But then along this axis number 3, I've just tuned TC prime to it a little bit higher. So now I first induce bond order at TC, and then I induce flux order at TC primed, and they both sort of switch on like this. Then in this region here, where where TC and TC primed are comparable, this is where they can actually switch on at the same temperature in a strongly 1st order transition. And it's strongly 1st order because you get this term and this term together, which both by themselves can already lead to a 1st order transition. And so you get this kind of onset. And then finally, if you go along the diagram here, then this is where TC primed is much higher than TC. And here something interesting happens again because of this third order term. So if TC primed is very large, then at some point this becomes negative, delta primed gets induced. Now if you've got delta primed here, then you see it adds a linear term for delta. So delta, of course, has this potential that this coefficient is still positive because we're somewhere up here above TC. So we expect it not to condense at this high temperature, but then because of this term, this adds a linear term to this potential, and then you can see that it basically will just induce some kind of linear term here and shift your minimum to some non-zero delta. So this is the way in which flux order always induces charge order, but not the other way around. So we can have bond order by itself, but we always have flux order inducing bond order. And that's because of this term here. Okay, so now back to the more complicated Landau theory with all of these different terms. So what you can see from this discussion here is what happens with this anisotropy, because I just assumed that all the three directions had the same order. So we need to look at this more complicated Landau theory to understand how we can get anisotropy, but it comes from this third order term. And to show you why.
Sorry, may I ask a question about your previous discussion here? When you have only odd power terms in delta prime order parameter, so how will you get this first order transition when your TC prime is larger than TC? Because delta itself is somewhat induced parameter and it will grow from zero. And basically you have only even powered terms in delta prime parameter.
So you mean
in the yes.
Actually, here it's a second order transition.
Okay, that's what my question.
Yes, it's a second order transition. That's what. It's a first order transition here because of the third order term, and here in this region. I've got some numerics later where you can see this, but yeah, first order here, and then it becomes second order here.
Yeah. That was my question.
Good. So yes, let's try and understand a little bit better how you can get this anisotropy from the third order terms. So the simplest way to see that is just to look at some different possible solutions for these six order parameters. So I'm going to start on the left over here and then work my way to the right. So on the left we have remember TC primed is larger than TC, but delta primed always induces delta. So we have both orders present on the left of this diagram, and let's assume that they're both isotopic. So you just have delta 1 equals delta 2 equals delta 3 equals some delta over square root of 3, and delta 1 prime equals delta 3 prime equals delta prime over square root of 3. Then if we plug it into this free energy F3, you just find it's beta 1 over 3 square root of 3 times delta cubed minus beta 2 over square root of 3 times delta prime squared.
Why the minus?
So,
because beta 2 is.
Yes, I'm assuming that beta 2 is negative, but the point is that I can always switch the signs of some of these to make that negative. So if I just switch the sign of delta 1, then I can make that term negative.
Yeah, but then you also switch maybe the sign of beta one.
That's right. That's right. So the only thing that matters is the sign of beta 1 times beta 2. And here we're going to assume that beta 1 times beta 2 is negative.
And why is it?
So beta, yeah, this sign of beta 1 and beta 2 affects the type of bond order that you have. So if you have beta 1 positive, then you want one of these to be negative and two of these to be positive. Whereas if you have beta 1 negative, you want all of these to be positive. And what that corresponds to on the kagome lattice is it's exactly the Star of David versus trihexagonal order. So if you have remember, you've got these three equivalent bonds along the hexagon. And if you have delta 1 equals delta 2 equals delta 3 larger than 0, then what this corresponds to is this kind of order. Now, on the other hand, if you have delta 1 minus delta 2 minus delta 3, then this means this bond is positive, this bond is negative, this bond is positive. So like this. So that's what this sign is basically determining. It's determining whether your bond order is Star of David.
So you can see that in the experiment, right?
And they can see that in experiment, exactly.
Both. Which one do you see?
In the experiment, they see the Star of David. So I think I showed you the slide, which is the one where you've got the sign, which is beta.
Negative. Beta 1.
That's beta 1. This one is beta 1 positive.
Positive.
1, 2, 3 is related to the M3M and 1 and 3.
So right, so delta 1, delta 2, delta 3 are there's 3 endpoints, and basically it's the amplitude along these 3 endpoints. Yeah. So okay, so this is the sort of most isotropic solution. That's solution 1. Now we move to the right of this phase diagram, and let's consider an isotropic solution which only has delta 3, and it's got delta 1 primed and delta 2 primed non-zero. Then this will give you 3 equals minus beta 2 delta prime squared. And what you can already see just by comparing these two free energies is that if, basically 2 is larger than square root of 3, and so if delta prime is very large, then you favor this term, right? And that's why this term 1 is basically this phase over here, and then 2 is this phase here that you get after you cross this this blue line. So that's just coming from comparing these different free energies, and you can see that this one is exactly one of these that big C6 symmetry. So that's just to show that you can get rotational symmetry breaking, and it's spontaneous rotational symmetry breaking in the absence of any kind of strain. And the other thing to notice is, now I mentioned that the magnetic field is important, right, for inducing the anisotropy. And the reason that the magnetic field plays a role is that the anisotropy is coming from this third order term here, that's delta prime delta. And in order for this term to even be active, you need delta prime to be there. So what the magnetic field does is it induces delta primed, and then the delta prime via this third order term induces anisotropy. So that's how we can get the magnetic field to actually induce anisotropy. It's just because it induces delta primed, which by this third order coupling.
Sorry, could you please, for this claim, to illustrate it, go back to your free energy, because it's magnetic field.
Yes.
Oh, okay, here.
So this is the magnetic field. So you can see that. So let's go. So you notice I placed this material over here in the phase diagram. The reason I did that is because if we assume the compound is here, then we only have delta. And so we never have any anisotropy because this third order term is not there. Now, we apply magnetic field that induces delta primed even in this region here, and that induces the anisotropy. So the magnetic field, it's always inducing delta primed when you have a delta.
Is it enough to have infinitesimal magnetic field, or you need some critical value for the field to have this symmetry break?
So we find that the symmetry breaking, it just sort of increases. I think I have some, maybe I don't have the slide, but it just increases as you increase the magnetic field, it increases more and more, but it increases from 0. Sort of an infinitesimal field is enough to induce this symmetry breaking. Yeah.
So in presence of magnetic field, why delta prime cube terms are not?
Oh, they would be in principle present. That's right. I'm just neglecting them because they're higher order. So we're assuming that, I'm going to third order here, where third order means third order and B is also like small in some sense. So I'm considering this to be a third order term as well, whereas the B delta prime to cube term would be fourth order. So, okay, so this is the just numerically solving that free energy that I presented before. And this is just without the third order terms, not much interesting happens, because without the third order terms, delta and delta primed aren't coupled. So you just have delta induced over here, delta primed induced over here, and both induced in the middle. And the dashed lines means it's a second order transition. Now with the third order term, it becomes more interesting. So you see this becomes a first order transition, and this one here too. And the black hatching denotes anisotropy. So this is exactly this kind of anisotropy that I was illustrating over here. So the third order term is responsible for the anisotropy. This is without the magnetic field. So you see if you cut along this axis, then you still have no anisotropy.
Sorry, but you have first at low in temperature, first you have a third order phase transition, next you will have a second. Yes.
There's a first order transition here and then a second order one. Yeah.
But in experiment, they don't see any second phase transition at low temperatures.
Well, we're assuming that the experiments are done somewhere over here, so actually they don't cross that line. And this is now adding in the magnetic field. So the magnetic field shifts these phase boundaries. But crucially, it's induced some anisotropy in the region where before there was no anisotropy. So it's basically shifted this thing to the right. And here you can see this is the blue curve is without magnetic field. The red curve is with magnetic field as a function of strain, and you see that the anisotropy increases as you apply the magnetic field. So now we can compare our Ginzburg-Landau theory to the experiments for these three different devices. So the pristine device, which is just in black, always has no anisotropy. The strain device gets anisotropy immediately at the charge ordering temperature because C6 is spoken explicitly, which is also what happens in the experiment. Then in the experiment with field, there's no anisotropy until you induce this delta primed, and then you get the anisotropy increasing, which is also more or less consistent with what they see in the yellow curve in experiment. And finally, if you have field and strain, then you just have some sort of smooth crossover where, I mean, this is for very small strain, and then it sort of crosses over to where the magnetic field induces the strain. The magnetic field induces the symmetry breaking. So first you have strain inducing the symmetry breaking, and then magnetic field induces the symmetry breaking. And that's also what's kind of seen in experiment. You have the small anisotropy first, and then it increases. Good. So in the final part of
another thing, like when you have different systems, the parameter of the Ginzburg-Landau theory can be different.
Yes.
In this case, you can even reproduce exactly the experiment result. I mean,
I'm not claiming that this is in any way quantitative.
Like, but you can change your parameter depend on the sample to reproduce this.
We can, in principle. I mean, the Ginzburg-Landau theory has a lot of parameters that, if you tune, you can fit to the individual samples. But that wasn't so much the point. The point was more to understand the physics behind it. Because this Ginzburg-Landau theory, it has a bunch of parameters. So really what you would want to do is you would want to compute the Ginzburg-Landau parameters from a microscopic model, which one can do. And then you don't have any fitting parameters. But as I mentioned, that's very hard to do for these kagome metals because you've got a very complicated band structure. So yes, in the last part of my talk, I want to mention a little bit about the different types of order parameters that you can get. And basically, the point is that I mentioned that we want some order parameters that transform under some irreps of this space group. And this is the list of all the different irreps of this space group. And we want to consider the different possible irreps that we could have and see if we can deduce which of the one is realized in experiments. So first of all, notice that, so TI is the translations. So notice that all of these are just trivial under translations. So we can already discard all of these 6 irreps because we want something that creates translational symmetry. So that narrows it down to these 4 different F irreps, which do create translations here. And I've illustrated these 4 different Fs here for the bond order and for the flux order. Okay, so this is just what they look like. And you can check that these transform as shown here.
But you also can even mix them. You can mix them. You can mix 4 of the irrep.
So what I'm going to consider next is some UREP for the bond order and some other UREP for the flux order, and yeah, combining them. So the important thing is that depending on which UREP we have, different terms are allowed in the Landau theory. So this is the multiplication table of these UREPs. And I mentioned before we're focused on the F's, so just look at the F part of this table. So if I take F times F, then I get this thing. And if I multiply this whole thing by F again, I get an A1 UREP. So that means that F1 cubed is allowed to be added to the free energy. On the other hand, if I try to take F3 cubed, well, F3 times F3 gives me this thing, times F3 does not give me A1.
But you can have F3 and F1.
Right, I could, but I can't have F3 cubed alone. And so basically, depending on which UREP we have, the third order term is either allowed or disallowed in the free energy. So this, remember, the third order term is really important to reproduce the experiment. So this tells us that the UREPs that are realized in the material must be either F1 or F2 for the bond order, because those are the ones that allow a third order term. So let me summarize that in a bit more detail here. So this table here is showing you what the allowed terms, third order terms are, where I'm assuming the bond order is from one of these four UREPs and flux order is from the F2 or the F4 UREP. You can show that flux order can only be F2 or F4, it can't be F1 or F3.
So you can even exchange, right? Switch the flux order and bond order. Like flip, like you can say as flux order is F2 and at bond order can be F2 and F4, and flux order is F1 and F2.
Flux order can only be F2 or F4.
Why?
You can show that just by looking at the space group. So basically, you write down all the possible types of flux order. So you've got this sort of 2x2 kagome lattice that's something like this. Okay, and then I can put fluxes everywhere. I can put a flux, you know, 5-1 here, 5-2 here, 5-3, 5-4, and so on. I can put in all these fluxes. See how these fluxes transform under the space group. Construct the UREPs. And you can show that for the flux order, what we get is we can get A2 plus 2A2 plus 2 plus 2F2 plus F.
Okay,
so you can see that you can't get F1 or F3 from it. Okay, so we have these different allowed third order terms. So the ones that I've circled in red have these delta cubed third order terms, which we need to get the first order transition. So that tells us that we have to be in one of these four possible combinations. And then we also need to couple to the magnetic field. It turns out not all of them can couple to the magnetic field. Only this one and this one can couple to the magnetic field. And so you can see that the intersection of the blue and the red is just one single possible order parameter combination. So we can use this knowledge from experiment to deduce that actually the bond order has to be this F1 order and the flux order has to be this F2 order. And that was just using this experimental input that is pretty well established. Okay, so let me summarize. I have considered correlated order to be at some kind of tipping point in these kagome metals, where small perturbations can lead to the C6 symmetry breaking. We've seen in the experiments that the transport anisotropy vanishes in stainless samples. And And it's only an out-of-plane magnetic field that can lead to a transport anisotropy. And we can understand both of these experimental features by some Landau theory that consists of an F1 charge order and an F2 flux order. And this is illustrating what these bond and flux orders look like on the kagome lattice. And finally, this is the phase diagram from the Landau theory. This is just numerically minimizing the Landau free energy, and you see that it's rather consistent with the experimental observations. So thank you for your attention, and I'm happy to take any questions.
Thank you, Glenn, for this nice talk. Time for questions. Yes.
My subject, some experiments insist that this ordering of kagome is 2 by 2 by 2.
Mm-hmm.
Do you consider 2 by 2 by 2 and not F order is E cross this interlayer order is also derived some more large symmetric property. Do you think about this kind of?
Right. So we've thought a little bit about the three-dimensional ordering as well. So yeah, all of my talk was just assuming it's two-dimensional and the instability is at the endpoint. But now there's some works that claim that actually the instability is at the L point in the Brunel zone, which is this 2 by 2 by 2 kind of order. And then you can do a similar Landau theory for the 2 by 2 by 2 order, but the allowed terms are different because basically the third order term of a 2 by 2 by 2 order is not allowed. So if you have this, you've got some momentum in the KZ direction for this out of plane order, and your KZ is pi, which is what you have got 2 by 2 by 2 order. Then if I take some delta cubed kind of term, then that has pi momentum along the KZ direction, and so it's not allowed anymore. So that's one big difference. If you have this 2 by 2 by 2 order, the third order terms don't occur. But what can occur is you can have, so let me call this order delta L because it's at the L point, and the KZ equals 0 is delta N. You can have a term that's like delta N delta L squared. That is allowed. And so you can build a Landau theory from these kind of terms, and they would have the same kind of features because, you can see that it's actually exactly the same free energy as we had, but it's delta L instead of delta primed. You can show that, you can map one into the other. So you can just replace all the delta primes by delta L's, and then the same analysis basically holds.
But then from that, you can see different experiment results.
Right.
When you control, we not have the standard bit anymore.
That's true. What this KZ equals pi does, it's basically alternating Stauf-David and tri-hex. So it's just, one layer will be the red one layer will be the blue one, and they alternate them. Yeah. But it's of course hard to see this with STM because STM is always only imaging the top layer. So STM can't really tell you what's going on along the direction.
Any more questions?
Yes. So how much of all this is specific to
Well, the one thing, of course, that we used was this whole sort of formalism with the different UREPs. So, what this assumes from the kagome materials is that you've got this 2 by 2 increase of the unit cell, and then you have C6 symmetry.
Well, the impression I had is that quite a lot of what you were presenting relied on the fact that you have big terms, and these big terms are basically something like delta times delta prime squared.
Yes, yes.
So presumably, if you have if such terms are allowed in other geometries, you would get similar results.
That's right. That's right. So what would be a little bit different in different geometries is let's see where this kind of relation that I was writing here, this decomposition of what kind of irreps you can get. This is really lattice specific, so that's a result for the kagome lattice. Now you can do it for other lattices with C6 symmetry, and you get some other list of irreps basically. But I mean, the formalism is the same, but you just need to calculate separately what the allowed irreps are.
I have a question. You at the beginning of your talk, you showed us the band structure, actual one, and the one which corresponds to type binding model, and you said that they're completely different. But then you introduce some simple order parameters on that nearest neighbors bonds, and the question is why it is working, but well, how to comment on it?
Right. So even though the DFT band structure is fairly complicated, the one feature it does share with this simple model is the location of the Van Hove singularities. So these actually, I don't know if you can really see it that well. Well, you can kind of see it maybe, that if you go along one of these endpoints, there's a Van Hove close to the Fermi level, not at the Fermi level, but very close. And the fact that we have these orders that have this 2x2 increase of the unit cell is coming from instabilities at the endpoint. So this is kind of consistent with both the simple model and the DFT band structure. So there's some DFT models where they really look at where the instabilities are, and they find either M or L point instabilities, which are the two options that I was talking about. Yeah.
So the related question. So this instability you are talking about, the Fermi surface instability, like it's responsible for the Cohen anomaly, and then the deep in the basically the kink in the resistivity. Can it be explained through the Cohen anomaly or Fermi surface instability in these systems?
Right. I mean, when you have this charge ordering with the increase of the unit cell, you have some kind of reconstruction of the Fermi surface. And I would expect that to change the resistivity.
But what I'm asking, since you're an expert in this field, so are there any studies like quantifying these susceptibilities, charge susceptibilities, and relating it to the resistivity of this?
Okay, actually quantitatively calculating the resistivity, not that I'm aware of.
I mean, you know the graph statement.
Yeah, I mean, in principle, it could be done. I don't know of any papers that have done it, but I've not.
I think you can do the following thing. You know the graph state, and then you use this graph state to do the DFT or to do the tie binding.
For simplicity, one can start with the tie binding.
So after you go to the phase, you use the tie binding that you have at this graph state. Do the calculation for transport.
Yeah, well, I would do the transport calculation probably in momentum space. I would just start from the Fermi surface,
yes.
And then do the kind of Fermi surface.
Depend on the size that you have, right?
Right, exactly. You put in some kind of order parameter that gaps out part of the Fermi surface, and once you've got the Fermi surface, the reconstructed Fermi surface, you can just do the sort of relaxation time approximation kind of ultimate calculation, I guess. Yeah. But I don't know sort of how well that agrees with the actual measured resistivity. I've not seen any comparisons.
So why do you need this Van Hove similarity for these transitions?
It's actually it's actually not particularly clear what what is going on, which is why we didn't try with these microscopic models.
But I think that usually when you have the Banach singularity, you have a lot of density of state to pair.
You've got a high density of states. It makes sense that something might happen, but the exact mechanism is not known. So it is not known whether it's something to do with phonons or whether it's a purely electronic transition. Yeah, there's been calculations of both type, both with phonons and without phonons.
And also you have the 2x2 extent, then you expect to see this from the endpoint.
Yes, the 2x2 increase is exactly what you would expect from the endpoint. That's right. So that's why it's thought that the endpoints are important and the high density of states there. But the mechanism is not.
Any other questions? Not, let's thank Glenn again.